Hello again. In my last video there, we reviewed the concepts associated with DC electricity just before we get into the concept or the theory behind AC electricity, and we talked about series circuits and parallel circuits and what the difference was between the two. Okay, here's a series circuit and here's a parallel circuit. Now, what's important with regard to the DC circuit is that you only have one way in which the current flows. So let's look at an example of what I'm talking about real quick. Typically in a DC circuit, a lot of times you would use a battery as your power source. Now let's take a look at this and see what's going on here. Okay, I have a battery which is represented right here, and then I've got a loop, which is my circuit. In other words, the wire, the conductors that are connected to the battery. Now with the battery, you only have really one way that current's going to flow. We have the positive, one side of the battery is got a positive charge, or it's the positive pole or terminal, and the other side of the battery has got a negative charge. In other words, it's got an excess of electrons, and this is the negative pole or terminal. This is actually created through a chemical process, an electrochemical process. So when we flip the switch and our current begins to flow, it's always going to flow in only one direction. It's going to go from the negative, where we have our excess of electrons, and it's going to try to go from the negative to the positive, where we have an absence of electrons, and the atoms as far as at this positive terminal are going to try to fill their valence shell with with electrons in order to stabilize. Okay, but the important point here is that this process, this flow of electricity never reverses itself. In other words, when we close the switch, the electricity will always flow when we're hooked up to a battery from the negative side to the more positive side. Okay, that is what's referred to as a DC or direct current type of a circuit. And it's called direct current because the current only flows in one direction, from the negative side to the positive side. Now, with AC, all of that changes, and one of the things that is of key importance with regard to AC circuitry is the idea or the theory of magnetism. Now, magnetism plays a very important role in this overall process of the generation of AC. In fact, without magnetism, we wouldn't have alternating current, and without alternating current, most of the nice things that we enjoy today, cell phones, communications gadgets, computers, would not be possible. All of those devices work off of alternating current. Now, one of the key concepts involved in alternating current theory has to do with magnetism. And what it says, or there's a law that says that basically when I have a wire, let's say that this pen represents a wire, and this wire or conductor, when it moves through a magnetic field, something happens. As the conductor cuts across the lines of magnetic force, in other words, cuts through the magnetic field, it's going to generate a voltage in my conductor. And if there's a complete path for current to flow, that's also going to cause a current to begin to flow. That's a very key concept in the study of AC electricity. The idea that if you have a wire, if you have movement, really. So let's say that this is my wire, this pen, and this is a magnet. Okay, then it's generating a magnetic field. If I move my wire back and forth so that it cuts across or cuts through the lines of magnetic force that are generated by the magnet, that's going to generate a voltage in my wire. I could also move the magnet. Okay, if I move the magnet up and down in such a way that now the magnetic lines of force are cutting across my conductor, that also would generate a voltage in my conductor, and if there was a complete path for current flow, we would have electricity flowing just by that process alone. Okay, most of our electricity that we use today is actually generated in this manner. That is to say that you have essentially a generator, an AC generator, where you have a conductor, or it could be a series of conductors. It could be a wire that's wrapped around itself a bunch of times, forming a sort of a loop or coil. And you have this conductor that's moving inside of a magnetic field. That's how most of the electricity that's used today in the United States is generated, through AC generators. The AC generator could be powered by any number of things. It could be powered by steam. It could be powered by gasoline. There's different ways to do it. But the key fact remains that the electricity itself is generated using magnetism, using a generator where you have either the conductors moving inside of a magnetic field, or you could have the magnet itself moving relative to the conductors. Either way, as long as you have magnetic lines of force cutting through the conductor, or cutting across the conductor, you're going to generate a voltage, which in turn will generate the flow of electricity. Okay, so a very crude visualization of this process I have made through this picture here, this little diagram. Let's say that this box here, this bar, represents a magnet, represents the North Pole. And this other box with the S in here represents the South Pole. And the little dotted lines represent the lines of magnetic force. Okay? If we put a conductor inside of this, and let's say that this loop of wire here is our conductor, and we start to, we cause the loop of wire to begin to spin around inside of this magnetic field, we're going to generate a voltage that is changing its polarity with each revolution. Actually, it's going to change polarity twice with each cycle, or each complete revolution of the conductor inside of this magnetic field. That generates an AC voltage and thus AC electricity. Okay, now let's look at this a little bit differently. Okay, I'm going to draw a graph, a very crude graph, but it still will give us the idea what I'm talking about. Okay, we'll say that the top side of this represents 10 volts negative, or 10 volts positive, and the bottom side of this represents 10 volts negative. Okay, well, with our DC circuit, when we just have it hooked to a battery, we're never going to go below the positive line. In other words, our polarity is going to be the same all the time. So what's going to happen when I close the switch is that the voltage is instantly going to reach its maximum. In other words, it's going to go from 0 to the maximum voltage relatively quickly, and it's going to stay at this constant level, let's say of 10 volts. It's not going to change. Okay? In an AC circuit, it's a little bit different. In an AC circuit, because you have the conductor and it's cutting through lines of force at a different rate as it spins, let's say at 90 degrees, it's not cutting through that many lines of force, of magnetic force, but it's actually running more or less parallel to the lines of force. Well, because it's running parallel, it's not actually going to cut through that many lines of force. But as it begins to spin and it moves another 90 degrees, it's going to be perpendicular to the magnetic lines of force, so it's going to be cutting through the magnetic lines of force at a relatively rapid rate, and thus it's going to generate its maximum voltage. Okay, so our AC signal may look something like this wavy line that I've drawn. Okay, with the first revolution to 90 degrees, well, let's pull my other diagram back up again. Okay. Let's say that let's say that we have our coil of wire so that it is basically sitting parallel. It's kind of hard to draw this out, but it's sitting parallel to the lines of magnetic force. It's this second box that I've drawn right here, the one that looks more like a square than a diamond. Okay, so right now, because this loop of wire is parallel to the lines of magnetic force, it's not cutting across anything, and so there's not really a voltage generated. In other words, we have 0 volts. But then we start to cause it to move, okay? And so now it moves in, let's say, a counterclockwise direction. Okay, so in a second diagram, we can conceptualize this. Okay, we'll draw our box again, and I may have to cut this off because I can only make these about 15 minutes or so in length, or it becomes I can't upload them. Okay, but let's say that we've moved it from that flat horizontal position to a new position where it's now perpendicular. Okay, we've moved it 90 degrees. It's hard to visualize this, but we'll say that this is, in other words, this is straight up and down this loop to where now it's perpendicular to the lines of force. Well, that 90-degree movement in the positive direction is going to generate our maximum voltage in this positive direction, this maximum of 10 volts. Okay? Then as it begins to move back to the perpendicular position again, the voltage is going to drop back down to 0. Then it's going to start moving in the opposite direction because it makes a big circle. And it's in another 90 degrees, it's going to hit its negative positive. So it's going to be at its maximum of 10 volts again, but this time it's in the negative direction. Okay, and then it goes back down to 0, where the loop of wire is no longer cutting across any of the lines of magnetic force, but is instead perpendicular to them. That's how an AC signal is generated. Now this poses a little bit of a problem because these quantities are different. This straight line that I have up at the top doesn't change, so this 10 volts is the same all the time. Is it the same when I generate an AC signal? No, it's not. We actually hit 10 volts just for a second, then in the positive direction, and then we start to go back in the other direction, and we hit the 10 volts negative. But it's not a constant 10 volts. So in essence, this quantity is different than the DC quantity. And we're going to have to find an equivalent level of resistance, and scientists have actually done that. So we'd probably have to generate a little bit bigger signal. Let me redraw this. Oops, not quite in phase there. It looks a little different, but that's okay. Because this AC signal is not at 10 volts all the time, we're probably going to have to generate a larger maximum voltage to be the equivalent of this constant 10 volts that we have with direct current. Okay, this is actually, there's different ways to conceptualize this. This right here is called the voltage peak. Let's say that it peaks out at, let's say this is 12 volts up here. So let me mark that. 12 volts, and then 12 volts again in the maximum direction, the negative. Okay, so we generate a maximum or peak voltage in one direction of 12 volts, then it goes back down to 0 volts, then it starts to cut across the lines of magnetic force again in the negative direction, and we have an opposite polarity of negative 12 volts. That is how the the AC voltage signal works. This is called a sine wave voltage. And we'll talk about how we can quantify this and find an equivalent number for this DC that matches up with this DC voltage in my next video. I hope you learned a little bit of something about AC voltages in this video.